Earth, what a great place to live. Space, it's not that nice. We've got the Earth's magnetic field, which deflects away the solar wind, which is not a very nice thing. And we've also got the Earth's atmosphere. Now, over 2/3 of it by mass is below the height of Mount Everest. So all these clouds you can see here, they're pretty much the bulk of the atmosphere, and it's pretty thin. So ultraviolet is what we need to be protected from. That's about 7% of the output of the sun. And this is a graph that comes from the black body radiation based on the surface temperature of the sun. It's something physicists came up with, and it puts the peak of the intensity in the visible spectrum, but nearly half of it is in the infrared, which a lot of that is heat. So here's a photo from the International Space Station at 400 kilometres high, about 4 times the height of this graph on the right, which is the international standard atmosphere. Now, pilots use this to get a basis for calculating their height based on the pressure. They use the surface pressure and then this standard atmosphere to figure out how high they are. And we can notice that the atmosphere is heated on the surface. That makes sense. But also it's heated up here, and the reason for that is the UV interacting with oxygen to form ozone, which not only protects us from the sun, but makes this inversion of temperature, which contains the weather in the tropopause, or below the tropopause. So you can see it here, that it's really flat on the ceiling. The thunderstorms will bump up against this, but luckily the tropopause stops them from developing out into outer space. Here's a photo I took in Antarctica. This cloud is in shadow, but much higher up in the stratosphere, these clouds are to do with the ozone hole being eaten up by CFCs. CFCs are also a really bad greenhouse gas, but luckily there's hardly any of them. Nitrous oxides, methane, and ozone in the lower levels is really bad. But carbon dioxide is the most plentiful greenhouse gas. It's only 400 parts per million. If you got all the air in the atmosphere over 1 square metre, it's about 10 tonnes. And if you figure out how much of that is CO2, it's 0.04%, that would go to about 3.5 metres. So it's about 4 kilos. So compare that 3.5 metres of CO2 to ozone, which is only a few millimetres if you brought it down to the surface. So even though these gases are really minute amounts, they make a big difference to life on Earth. Water vapour is actually responsible for over half of the greenhouse effect, and clouds make a huge difference as well. But water vapour only lasts in the atmosphere for a week or two before the weather rains it out somewhere. And the amount of water vapour that can be held increases exponentially with the temperature. So that's why you find it all near the tropics, where you get most of the heavy rainfall, and close to the surface. This is the heat budget for Earth. You can see the sun coming in. The actual rate, if you're facing straight towards the sun and you're on a spaceship, is about 1,000 watts higher than this, but this is averaged over day, night, summer and winter. And also this is an average, like not taking into account what the surface is. So 2/3 of the Earth is water. You'd expect more evapotranspiration there, and thermals are going to be stronger in the middle of the summer in the Australian desert. But what's really important in this diagram is that the biggest amounts of heat transfer is actually going from the atmosphere to the Earth and back again. That is a good regulating thing, because otherwise when it got to be nighttime, it would be extremely cold, extremely fast. You can notice there's a lot more of that if you're on a mountaintop, where there's thin air above you and no cloud cover. As soon as the sun sets, it gets really cold. But if you're on the coast and it's more humid, there's not such a difference. If you're in space on a satellite, as soon as you go behind the Earth's shadow, it starts getting cold really fast. If you wanted to calculate how warm the air would be without a greenhouse layer, greenhouse gases, then you can do it based on the energy hitting the sun, which appears as a disk, and the energy going out from the Earth, which is proportional to its temperature to the power 4. So it's quite sensitive. If the temperature changes a little bit, there's a lot more outgoing radiation. That, of course, doesn't account for it being trapped by the greenhouse gases, clouds, and water vapour. So, doing some simple calculations, using 31% for the albedo, which is how much is reflected off clouds and ice caps and anything shiny, we get a theoretical temperature that the Earth should be, average, of minus 19 Celsius. That compares to what we observe, which is about 14 Celsius averaged over the Earth, a difference of 33 degrees. If you change the albedo to 0, that'd still be a difference of 9 degrees. So here we've got a visible image. Wind is exaggerating it a bit. It's pretty dark over here. You can't really see these clouds. It'd be like looking at the moon and trying to see the dark side of the moon. And you can see that the clouds, obviously where they're white, it's going to be reflecting a lot more of the sunshine back into space, and the white ice caps as well. But if you look at the infrared, it's obviously hottest in the centre of Australia, where you've got sun shining on the hot ground. But it's cold in the tropics, where the sun's hitting straight on, but it's hitting the tops of these clouds. So think about what you see in the satellite is the energy that's coming from the Earth to the satellite. So some of the energy underneath, obviously is very hot in the tropics, but the heat is being trapped underneath that cloud and being reflected back down again. Applying that to paragliding, this was a really good day at Beachmont. There was a thin layer of misty fog in the morning, but quite a lot of cloud cover, and the wind's generally from the east. So thinking about it coming off the ocean staying warm all night, there won't have been much of a chance for the air to get, well, the air would be warm at the surface and it's nice and unstable, keeping a warm surface. And the cloud cover, scattered cloud cover, would also help it not get so cold over land. So as soon as the sun came up, I was surprised at how fast the cumulus started developing.